Hey guys, in the last lecture we had a view on the continuous uniform distribution. What did we do? We found its expectation first, then we found its variance by expectation of x square variance, and then we did one sum that was regarding uniform distribution. Now let's start with exponential distribution. So going ahead, how do you denote a random variable is follows exponential distribution? It is denoted as this. X is nothing but my random variable and lambda would be my parameter of exponential distribution. Okay, so yeah, this is how you denote. So basically then we viewed its PDF. PDF is probability density function, which is denoted by f of x. It is stated as lambda e raised to minus lambda x. Okay. What did we did for other distributions? We found its CDF, then we found its mean, we found its variance. We are going to do these exact same steps even for the exponential distribution. So going ahead, what do you mean by CDF? CDF is capital F of x. It is nothing but probability of x less than equal to x. So basically it's nothing but less than equal to x. So it has the maximum value of x. What would be the minimum value? Exponential distribution is a distribution where x can take value greater than 0 only. It goes till 0 till infinite basically, okay? So the maximum value it can take is infinite, but in case of CDF it is x, but the minimum value is 0. So it would be 0 here. Lambda e raised to minus lambda x. So I can even write this as f of x dx. Let's substitute the value of f of x. It would be nothing but lambda e raised to minus lambda x dx. Okay. So let's take lambda common. We are integrating with respect to x. X is in this term, not in the lambda term. So basically I can take my lambda common. Lambda integration of 0 to x e raised to minus lambda x dx. Okay, so e raised to ax integrations formula is nothing but e raised to ax upon a. Similarly, here a is nothing but minus lambda. So I can write this as e raised to minus lambda x upon minus lambda. A is nothing but my minus lambda from value 0 to x dx. Let's simplify this. Lambda basically gets cancelled. Okay, moving ahead, it would be nothing but minus of e raised to minus lambda x 0 to x. So what we did, we substitute the upper value minus the lower value. So I'm left with minus e raised to minus lambda x minus e raised to minus lambda 0. So which would be nothing but e raised to 0, right? Okay, so I'm left with minus e raised to minus lambda x minus 1. If you substitute e raised to 0 in your calculator, it is 1. So you can try it and substitute. But if you want to learn it directly, you can even learn it that e raised to 0 is 1. Going ahead, minus, let me take minus common. So I'm left with minus of e raised to minus lambda x plus 1. Let me arrange this in a better format. It would be nothing but 1 minus e raised to minus lambda x. So this is my CDF value. So what does my CDF denotes? Probability of x less than equal to x is nothing but 1 minus e raised to minus lambda x, right? As I know that probability of x less than equal to x, is equal to 1 minus probability of x greater than x, right? Why? Because this value plus this value is equal to 1, right? So basically I can write that this value will be nothing but 1 minus this value. So let me substitute probability this value here. So I will get 1 minus probability of x greater than x is equal to 1 minus e raised to minus lambda x, right? There is 1 minus here, 1 minus here. So basically I'm subtracting both sides by 1. I get minus probability of x greater than x is equal to minus e raised to minus lambda x. What did I do? I subtracted 1 on both sides. Now in the next step, I'm going to divide by minus 1. So yeah, we are left with probability of x greater than x is equal to e raised to minus lambda x. Okay, this is my second formula. Even logically, you can say that probability of x greater than x plus probability of x less than equal to x must be 1, right? This is some basic probabilities. So even you substitute this value, that is e raised to minus lambda x plus 1 minus e raised to minus lambda x. I will still get 1 because this and this cancels and I'm left with 1. So I can prove it either ways, but it's okay. Okay, going ahead. There is one formula for median. So what is the formula for median? It is nothing but log of 2 upon x. The derivation of median is not important, so we are not doing it in detail, and it is even some complicated one. Okay, so yeah, so basically let's take an example of an exponential distribution to understand. So if x follows exponential with parameter 5, I can basically say that my PDF, what is the value of PDF? PDF is nothing but lambda e raised to minus lambda x. So instead of lambda, I can substitute 5 because if you see here, we denoted this as lambda, right? Instead of lambda, basically now I'm just writing 5. So I can write this as 5 e raised to minus 5x. Okay. What would be my CDF? CDF formula is nothing but 1 minus e raised to minus lambda x. Therefore, my CDF would be nothing but 1 minus e raised to minus 5x. Instead of lambda, I'm just writing 5 because this denotes lambda. Okay, this is an example how you write it. Like any other sums or any other derivation, let's find its exponential and that is expectation and variance. But before doing expectation and variance, there are some formula which you must learn. These formula are not given in tables book, so you have to learn. Okay, this formula is known as gamma function. Okay, so what do you mean by gamma function? Understand this. If integration from 0 to infinity, okay, 0 to infinity, x raised to alpha minus 1 e raised to minus beta x dx, then my gamma function is nothing but gamma of alpha upon beta raised to alpha. This is my gamma function, okay? So let's take an example to understand. So if my value is nothing but x raised to 2 e raised to minus 5x dx, then if I compare these two equations, what would be my alpha and what would be my beta? Guys, take care. This is 2 and I want alpha minus 1. So basically I can write 2 as nothing but x 3 minus 1. Okay, take care about this thing. So now my alpha is 3. Do not directly jump into the conclusion and write alpha is 2. And beta is same. So basically beta is nothing but 5. So this would be nothing but gamma of 3 upon 5 raised to beta. What is gamma of something? What is this? How do you calculate? You must be ignorant about these terms, right? But I can say that gamma of any number, so let my number be a, is nothing but a minus 1 factorial. So here it would be nothing but 3 minus 1 factorial, which is nothing but 2 factorial. Okay, 2 factorial upon 5 raised to 3. Okay. What is factorial? If you forgot, I'm just explaining you once again. We did it about that then also. 5 factorial is 5 into 4 into 3 into 2 into 1. I can also write this as nothing but 5 into 4 factorial, because 4 factorial will be also 4 into 3 into 2 into 1. So yeah, this is the explanation. This you must have done in colleges or school. What do you mean by factorial? But then also it was just for your understanding. So 2 factorial is nothing but 2 into 1 upon 5 raised to 3. If you feed this in your calculator, it would be nothing but 0.016. Okay. So gamma of a is nothing but a minus 1 factorial. Okay. Let's go ahead. You must know these formulas. Okay. And even if you forget this formula, this is written in page 5 of my actuarial tables. So let's go ahead and now find my expectation and variance. So starting with expectation. So what is my expectation? Expectation nothing means average, or I can say mean. It means one and the same. So it would be nothing but x into PDF. So f of x summed over all values, which is nothing but integration of all the values of x. As I stated above, if you forgot, my values for exponential distribution will not be nothing but greater than 0. So I can say that my minimum value would be 0 and my maximum value greater than 0 is nothing but till infinite. So my maximum value would be nothing but infinite. Okay. What is fx? Fx is nothing but x into lambda e raised to minus lambda x dx. If you see, it is even written right here. Yeah, PDF this. Okay. Going ahead, let's solve it. I can take lambda out because it's a constant, since we are integrating with respect to x and it does not have an x term. So basically lambda is a constant. Lambda integration of 0 to infinity x e raised to minus lambda x dx. Okay. So I took lambda out and I'm left with x into e raised to minus lambda x dx. How do I solve this part? I just did it before, right? I can write this as nothing but my gamma function. So I can write this as x raised to 2 minus 1 e raised to minus lambda x dx. If I compare this with my gamma function, which is nothing but this, Okay, if I compare with this, I can say that my alpha is 2, right? 2 minus 1, alpha minus 1, 2, and beta is equal to lambda. So I can use now this formula. Using this formula, what is my alpha? Alpha is 2, so into gamma of 2. What is beta? Beta is lambda. What is alpha? Alpha is 2. So basically, I can cut this and this, right? And I am left with gamma of 2 upon lambda. What is gamma? Gamma of A? It is nothing but A minus 1 factorial. So here it would be 2 minus 1 factorial, right? Which is nothing but 1 factorial upon lambda. What is 1 factorial? 1 only. 1 into nothing, because it would be 1 by lambda. So basically, I can say that uh, hmm, basically I can say that my expectation of x is nothing but 1 by lambda. Okay, we found expectation of x. Now we will find variance. How do I find variance? Similar step, which is nothing but expectation of x square minus expectation of x the whole square. We have expectation of x, we just want expectation of x square, which is nothing but this term. So let me write down expectation of x square. It would be nothing but x square into f of x summed over all values of x, which is nothing but 0 to infinite dx. Similar steps, integration from 0 to infinite x square into f of x is nothing but, what is f of x? If you see above, it is nothing but lambda e raised to minus lambda x, right? So let me write that now. Lambda e raised to minus lambda x dx. These are similar steps as expectations, okay? Instead of just x, it is x square here. So going ahead, I can take lambda common because it does not have an x terms, and since it does not have an x term, it is considered to be a constant. So I can take my lambda out here. So I'm left with lambda integration from 0 to infinite x square e raised to minus lambda x dx. Okay. Now let us compare similarly our answer with my hmm, yeah. Similarly, now I can compare my answer with gamma function. So what would be my value of alpha and beta? Beta is same lambda. What will be alpha? This would be nothing but x raised to 3 minus 1. Therefore, alpha would be 3. Comparing. Now I can use this formula instead of this. So let me just substitute it. It would be nothing but lambda gamma of alpha upon beta raised to alpha. What is alpha? Alpha is 3. What is beta? Beta is lambda raised to alpha. What is alpha? Again 3. I can cut this and make lambda square. So I'm left with gamma of 3 upon lambda square. Going ahead, what is gamma of A? It is nothing but A minus 1 factorial. Therefore, even I can write this as A minus 1 factorial. I can write this as 3 minus 1 factorial upon lambda square, which is nothing but 2 factorial, right? What is 2 factorial? 2 into 1 upon lambda square. It is 2, right? And the denominator remains as it is, that is lambda square. So I get my expectation of x square as nothing but 2 by lambda square. Now using the formula of variance, what was the formula of variance? Variance was nothing but expectation of x square minus expectation of x the whole square, right? I know the value of expectation of x square, which is nothing but 2 by lambda square. What is expectation of x? It is nothing but 1 by lambda. So let us write there minus 1 by lambda. Its square, expectation of x square, so 1 by lambda square. So I get 1 by lambda square. If I simplify, it is nothing but 1 by lambda square. Okay, so I got even my variance aspect now. Pretty great, right? So there is one more distribution similar to the exponential distribution. So let us study that distribution in this only. It is known as gamma distribution. So guys, I know this might be a bit heavy. So you could take your break whenever you want because it is a recorded lectures. And even one more thing, I know you have to watch these lecture once or twice. Watch these lectures once or twice and then proceed with learning your all the derivations. It would be important. I'm again and again repeating, I know that learn derivation plus. Please do it, guys. Okay. So gamma distribution, how do I denote gamma distribution? X follows gamma, GA with parameter alpha, comma, lambda. What is X? X is my random variable. What is alpha? Alpha is first parameter of gamma distribution, right? What is lambda? Lambda is my second parameter. So basically, as above, it took only one parameter, that is lambda. Exponential only took one parameter, lambda. Here there are two. Okay. Right? Then what did we do? We denoted its PDF. So let us denote that now. PDF, or I can say f of x is nothing but lambda raised to alpha upon gamma of alpha x raised to alpha minus 1 e raised to minus lambda x. Okay, this is my PDF. You could even see these PDF mean and variance in the tables book. Every distribution which we do in chapter 4, or you can say CS1 chapter 1, can be viewed in your uh, tables book. So you do not have to worry if you forget these PDF because you can directly see it from your tables book. Okay, going ahead, every time what we did after writing PDF, we calculated CDF. So let us do that. CDF, what do you mean by CDF? It is nothing but P of x less than equal to x, right? But for gamma distribution, there is no CDF. There is no CDF at all. So we won't be doing CDF of gamma distribution. Then after writing CDF, what did we do? We always calculated its mean. So let's now calculate its mean, or you can write expectation, or you can write average, anything you want to write. Okay, so what is the formula? It is nothing but x f of x summed over all values of x, right? Even here x would be greater than 0 only. So for all the values of x is nothing but 0 to infinite, we are integrating with respect to x, so dx. Going ahead, let me write what fx is. So fx is nothing but lambda raised to alpha upon gamma of alpha x raised to alpha minus 1 e raised to minus lambda x. Okay, so this term basically does not have a term of x. Since it does not have a term of x, I can say that this is a constant, I can take my constant out. So yeah, let me take my constant out. I'm left with lambda raised to alpha upon gamma of alpha integration of 0 to infinity x into x raised to alpha minus 1 e raised to minus lambda x dx. Okay, I can club these two part. How? So basically 2 raised to 1 into 2 raised to 4, I can basically write 2 raised to 5. So the property is a raised to m into a raised to n is nothing but a raised to m plus n. Okay, this is the property of indices. So yeah, I will use this since a is constant, even here x is constant. I'll basically add m and n. So I'm left with x raised to m. M is 1. N is nothing but alpha minus 1. So basically 1 and 1 gets cancelled and I'm left with x raised to alpha. Okay. E raised to minus lambda x dx. Okay. Similarly, even this I can compare it with my gamma distribution, gamma function, sorry, not distribution, gamma function. Let me just copy paste the gamma function. Yeah, gamma function. Now let's figure out the values of alpha and beta. Beta is simple, okay? Comparing this and this, I can get beta is nothing but lambda. So I can write lambda here, okay? Now I always stated I compare it with alpha minus 1. So I always write this in that term, okay? So I now state that alpha is nothing but alpha plus 1, okay? So yeah, I got my value of alpha and beta. So basically I can now use gamma function. What will I get? I'll get lambda raised to alpha upon gamma of alpha into gamma of alpha, right? So alpha is nothing but alpha plus 1. So I can write this as uh, gamma of alpha plus 1 upon beta raised to alpha. What is beta? Beta is lambda. Lambda raised to alpha. What is alpha here? Alpha here is nothing but alpha plus 1. Okay. So alpha plus 1. I can now simplify this. I can write this as nothing but lambda raised to alpha upon gamma of alpha into what is the property of gamma of alpha or gamma of a? It is nothing but a minus 1 factorial, right? So I can write this now as nothing but alpha minus 1 factorial. Similarly, even I can write this as nothing but alpha factorial, and this would be lambda alpha plus 1. I can now cancel this, and remainder term is lambda, and I will be left with alpha factorial upon alpha minus 1 factorial into lambda. Okay, so I can write alpha factorial as nothing but alpha into alpha minus 1 factorial. Similar example, 5 factorial is nothing but 5 into 4 into 3 into 2 into 1, right? So I can write this as nothing but 4 factorial. So this is nothing but n factorial, n into n minus 1 factorial, right? So I can write now this term as nothing but alpha into alpha minus 1 factorial upon alpha minus 1 factorial. Denominator remains as it is. I can cut this now. So I'm just left with alpha by lambda, expectation of x. Okay, I got expectation of x. I know this was a big derivation. Leave it. Now let's find variance. Variance, similar steps, which is nothing but expectation of x square minus expectation of x the whole square. I have expectation of x, I just want expectation of x square. So let us find that now. Okay, expectation of x square. It would be nothing but x square into f of x, right? Summed over all the values of x, which is nothing but 0 to infinite, right? So next step would be nothing but substituting our values. So what is f of x? Lambda raised to alpha upon gamma of alpha x raised to alpha minus 1 into e raised to minus lambda x, right? So lambda raised to alpha upon gamma of alpha into x raised to alpha minus 1 e raised to minus lambda x dx. If you see, this term is basically a constant, right? If this term is a constant, I can take it out. So I can take this term out here. So I am left with lambda raised to alpha upon gamma of alpha integration from 0 to infinity x square x raised to alpha minus 1 e raised to minus lambda x dx, right? Similar steps, I can combine these two now. What was my indices property? It was nothing but a raised to m into a raised to n is nothing but a raised to m plus n. So I can write this as a raised to m plus a raised to m plus a raised to n. So n is nothing but alpha minus 1. Alpha minus 1 plus 2 is nothing but alpha plus 1, right? E raised to minus lambda x dx. Now basically I can compare this with my gamma function. Similar steps as expectation. Okay guys, so let me just copy paste it now. So now I'm comparing it with my gamma function. What do I get? I get my beta as nothing but lambda. What do I get? Alpha. I can now write this as x raised to alpha plus 2 minus 1. Now comparing this part and this part, this part and this part, I basically get my alpha as nothing but alpha plus 2. Okay guys, these steps are quite similar, I know that. So I'm going a bit fast. Lambda raised to alpha upon gamma of alpha into, I can write now this in this format, this format, right? So how do I write this? Gamma of alpha, what is alpha? Alpha is nothing but alpha plus 2. Beta raised to alpha, so beta is nothing but lambda. So lambda raised to alpha, what is alpha? Alpha is nothing but alpha plus 2. Okay, I wrote this. Now let us simplify similarly. I can write this as alpha minus 1 factorial, and similarly when I can write this as alpha plus 1 factorial, right? What did I use? Which property did I use? I used the property of gamma of a is nothing but a minus 1 factorial. Okay, basically I used that property and got my answer. Now going ahead, upon lambda raised to alpha plus 2. So if I cut this, I'm left with lambda square. So I'm left with alpha plus 1 factorial upon alpha minus 1 factorial into lambda square, right? So now I can write alpha plus 1 factorial as nothing but alpha plus 1 into alpha factorial, and I can write this as alpha minus 1 factorial into lambda square. Similarly, even I can write alpha factorial as nothing but alpha into alpha minus 1 factorial. Which formula did I use? I use gamma of A is nothing but A minus 1 factorial. Similarly, A minus 1 factorial is nothing but A minus 1 into A minus 2 factorial. Okay, these are the formulas I used. Now basically I can cancel this, and I'm left with expectation of x square as nothing but alpha into alpha plus 1 upon lambda square. Going ahead, we found expectation of x square. Now we have to go for variance. What is the formula for variance? It is nothing but expectation of x square minus expectation of x the whole square, right? What is expectation of x square? It is alpha into alpha plus 1 upon lambda square minus what is expectation of x? It is alpha by lambda, right? So yeah, let me write alpha by lambda. Expectation of x the whole square. So expectation of x is alpha by lambda the whole square, right? Going ahead, I get, let's just multiply alpha with respect to each term. I get my answer as alpha into alpha is alpha square plus 1 into alpha is alpha minus alpha the whole square is alpha square upon lambda square. Now basically let's take the numerator common because the denominator is same. So alpha square plus alpha minus alpha square upon lambda square. This and this gets cancelled. So I'm left with variance is equal to alpha by lambda square. Okay. You remember why did I introduce gamma in this only? There was one reason, right? It is linked to my exponential distribution. How it is linked, I will show you now. So gamma is basically linked to exponential distribution when alpha is equal to 1. Okay, and lambda is equal to lambda. Then gamma is nothing but exponential. If you want to prove, we will even prove. Let us prove first expectation of x. What did we get expectation of x under gamma? We got this as nothing but alpha by lambda, right? So if you see here, we got this as alpha by lambda, right? So I can write this as alpha by lambda. Now let's put alpha as 1 and lambda as lambda only. So I get this as nothing but 1 by lambda. If you see expectation of x, it is nothing but 1 by lambda for exponential distribution. See, I did exponential distribution here. I started with exponential distribution and I found expectation of x as 1 by lambda, which is nothing but what we just stated here. Even you could prove for variance and even for my CDF, even for my PDF, anything. You could prove this by substituting alpha as 1 and lambda as lambda. You will exactly get the same PDF of exponential, CDF of exponential and variance of exponential. So yeah. Okay. Gamma is linked to another distribution as well, which is known as chi-square. So gamma is linked to exponential when alpha is equal to 1 and lambda equal to lambda. We proved it for exponential. We could even prove it for variance, CDF and PDF. It's not necessary to prove, but then also I proved it for one. I proved expectation for you. But if you're keen on knowing even the variance CDF and PDF, you could prove it for yourself. It's okay. It is damn easy. Going ahead, chi-square. So when gamma is chi-square, when alpha is nothing but V by 2 and lambda is half, then I can say that my gamma would be chi-square. What is V? V is nothing but degree of freedom. What is degree of freedom? Just ignore this as of the moment. Once we go ahead in the portion of CS1, we will understand what degree of freedom exactly means. We will even use these degree of freedom in our calculations. So yeah, going ahead. So what would be my PDF? PDF. Let's first write the PDF of gamma. So PDF of gamma is this, right? So let me copy paste it. I'm lazy, so I'm copy pasting, but you have to write a full, make a notebook and write it. So instead of lambda, I will put half, and instead of V alpha, we'll put V by 2. So I'll get this as nothing but half of V by 2, the whole raised to V by 2 upon gamma of V by 2 into x raised to alpha is nothing but V by 2 minus 1 e raised to minus lambda. Lambda is half and x remains as it is. So yeah, this is the PDF of chi-square. So this I got it. This is a new distribution altogether, okay? So yeah, let's now find expectation of x. Under gamma, what was my expectation of x? It was nothing but alpha by lambda, okay? So let me write this as alpha by lambda for gamma. This is for gamma and this is for chi-square, okay? So what would be my expectation of x? Alpha, let me substitute alpha and lambda, I will get expectation of x. So alpha is v by 2. What is lambda? 1 by 2. So basically I can write this as nothing but into 2 by 1. What did I do in this step? Basically I took reciprocal. This was divided by half. How can I write this in multiplicative sign? Basically this becomes this and this becomes this. Reciprocal. So 2 by 1. So this gets cancelled. I'm left with v. So expectation of x is v for chi-square. Similarly, let us find variance. What did we get variance of gamma? As nothing but alpha by lambda square. Let me substitute each value. I'll get, oh, I'm so sorry, I was about to write this with a black pen because I've denoted, wherever there was gamma, I denoted with a black. So yeah, alpha by lambda square. This is for gamma. Now writing it for chi-square. I'll get alpha as v by 2 and lambda as 1 by 2 square. 1 by 2 square. So I can write this as v by 2 divided by half square. What would be half square? It would be nothing but 1 by 4. Okay. So I can write this as nothing but v by 2 into 4 by 1. Wow, how reciprocal division sign becomes multiplicative sign when we reciprocal it. So this becomes 2 and I'm left with 2 of v. Okay, variance of x is nothing but 2 of v. This is for chi-square. Okay, we proved it for chi-square. We proved that gamma is linked to exponential as well as chi-square. Then we found mean and variance for gamma and even exponential. And so we will be done with this lecture. In the next lecture, we will see another distribution. So, yeah, thank you. Hey guys, this lecture is basically an extension of the previous lecture. What did we do in the previous lecture? Previous lecture, we derived our expectation and variance of exponential distribution. We also derived, yeah, so we also derived CDF of it, and then we derived expectation and variance of exponential. Then we went on to the gamma distribution. We wrote the formula, PDF, everything. We derived its expectation and variance. We didn't derive CDF because basically there is no CDF for gamma distribution, okay? So yeah, then we linked gamma distribution to exponential distribution. When gamma distribution is an exponential distribution, it is when alpha is equal to 1 and lambda is equal to lambda. Okay, I proved it for expectation of x. If you want to prove it further, you could even prove it for variance, CDF, and PDF. Okay, going ahead, we even stated that gamma distribution is related to the chi-square distribution when alpha is equal to v by 2 and lambda is equal to 1 by 2. Okay, so now whatever we are doing, it is nothing but an extension of what we did in the previous lecture. So starting with it, let's start with waiting time distribution. So this is not a new distribution. Basically, it's just a combination of Poisson and exponential distribution. It's not a new distribution at all. So basically, what does my waiting time distribution basically says? It says that if x, that is my random variable, follows Poisson distribution with parameter lambda, then my waiting time, which is t, waiting time between two consecutive events. Okay, so I defined one term t, which is waiting time between two consecutive events. So if x follows Poisson distribution and I were to calculate the waiting time between two events, then basically my waiting time follows exponential with the same parameter lambda. Okay, so let me take an example. Okay, so I work in an insurance company basically, and I work in a department where I handle grievance of customers. Okay, so I start working at 9 a.m. and till suppose 6 p.m. Okay, so I am calculating the probability that my waiting time that I receive the first call is less than or greater than 9 a.m. or greater than 10 a.m. So basically, I would be finding the probability that I receive no call between 9 a.m. and 10 a.m. and then at 10 a.m. I receive a call. So that's what my waiting time says. Waiting time states that between 9 a.m. and 10 a.m. I receive no claims or I receive no calls, and at 10 a.m. I receive a call. This is what waiting time states. So if my calls follows Poisson distribution, let me write it. Yeah. So if my calls follows Poisson with parameter 20, so basically I receive 20 calls in a day. Okay, then my waiting time between two events is nothing but exponential with the same parameter 20. Okay, so let us expand this further. So if this is for a day, right? If I'm measuring for an hour, if I'm measuring for a month, I stated an additive property. What was my additive? Additive property. Yeah, let me just see. Yeah. Hmm. Yeah, I stated an additive property as well as change of units. These were the two additional property of the Poisson. Let us see change of units. What does change of units says? If x follows Poisson per unit time, then xt follows Poisson with parameter lambda t in t unit time, right? So this was my change in units, the second property of the Poisson distribution. So we would be using that thing now. So now if I'm measuring per hour or something like that, so x follows Poisson with parameter lambda per day. If I'm following per hour or per t hours, my x would follow Poisson with parameter lambda t, right? This is what my second property stated. If you can see, I've already stated it right here. Xt, that is xt follows Poisson with parameter lambda t. So what would be its PDF? PDF of Poisson is nothing but e raised to minus lambda, lambda raised to x upon x factorial. So if x follows Poisson, then my PDF would be nothing but e raised to minus lambda, lambda raised to x upon x factorial. Similarly, if my x follows Poisson with parameter lambda t, then my PDF would be nothing but e raised to minus lambda t raised to x upon x factorial. What did I do? Basically, instead of lambda, I just wrote lambda t because now my parameter is lambda t rather than lambda. Okay, so going ahead, you understood what is waiting time. Waiting time is nothing but yellow part, that I do not receive a call between 9 a.m. to 10 a.m. That is my waiting time between I receive a call. Therefore, this is waiting time. And then I extended further that what my Poisson is when I'm measuring in t hours or t unit time, right? So I saw that. Now, basically, let us prove that why it is an exponential distribution. Okay, so what does my waiting time states? Waiting time states that I receive no claims. X is nothing but number of claims, right? In at least t hours or t unit time, right? Which is I have to wait for at least t hours, and which I receive zero claims. So basically, I receive zero claims is nothing but p raised to x is equal to 0, right? what is x is equal to 0? This is my PDF. So instead of x now I can write basically x is equal to 0. So I can write here 0 and I can write here 0 factorial. Anything raised to 0 is 1. So I get probability of t greater than t is nothing but e raised to minus lambda t. Anything raised to 0 is 1. Anything divided by 0 factorial or 0 factorial is basically 1. So I can write that probability that t greater than t is nothing but e raised to minus lambda t. If you see this, and what did I write for probability of x greater than x under the exponential part? It is exactly the same. See this? It is exactly the same. So let me just copy paste this. Where was I here? So this is of exponential distribution. Okay, and this is my waiting time. If I compare these two, I can say that this is exactly same. So I can say now that my waiting time follows exponential distribution. Okay, this was my waiting time. Basically, I stated what my waiting time is. Then I wrote Poisson. I established a better part for Poisson per t hours or per t unit time. Then I proved that basically my waiting time follows exponentially. This was my proof. So now I can say that my waiting time follows exponential. So if a question comes regarding to find probability that my waiting time, that is nothing but t, is at least 5 hours, I can use the formula of t is exponential, which is nothing but 1 minus e raised to minus lambda x, where x would be nothing but 5. So basically I could use this formula of the c. This formula is basically CDF of exponential. Similarly, probability that my waiting time would not be more than 5 hours is nothing but e raised to minus lambda 5, or I can say e raised to minus lambda x, where x is nothing but 5. This is nothing but this aspect, right? And let me show you the CDF that it's exactly the same what I just wrote. Okay, see here. CDF is this only. So basically, if my waiting time take at least some hours, then I could use the CDF of exponential. And if it takes greater than some hours, I could use 1 minus CDF. So this part. So any questions come relating to the probability of waiting time, you always use exponential distribution. Okay. So let's do one or two sums so you get an hang over this part as well. So going ahead. So basically, claims in and general insurance 24-hour call center follows Poisson process with rate of 3 per hour. So basically, X is nothing but calls, or you can say claims in a general insurance call center, right? X follows Poisson. It is written it follows Poisson, right? With parameter of 3 per hour, right? And basically, I want to calculate the probability that next call arrives after half hour. So I want to find probability that my next call arrives after more than half hour. So next call arrives. So between one call and second call, it is greater than half hour. This is exactly the concept of waiting time. Waiting time measures the time between two consecutive events. So I can say that now my t follows exponential with parameter 3. T is nothing but my waiting time. Okay. So what is my probability that my next call arrives after more than half hour? So this. So I want to find using the direct formula which I stated here. It is nothing but e raised to minus lambda x. So yeah, using that formula now. E raised to minus lambda x. What is lambda and everything I know? Since it follows exponential with parameter 3, my lambda is nothing but 3. What is my x? X is half. So which is nothing but e raised to minus 1.5. If I substitute this in my calculator, I'll get my probability as this. So this means that there is 22% probability that I do not receive a call for 30 minutes, more than 30 minutes. Okay. Similarly, let's solve one more sum. If the reported claims follows Poisson 5 per day, so X is my reported claims. If it follows Poisson with 5 parameter per day, okay, we are assuming 24 hours, okay. Calculate the probability that less than 2 claims are reported on a given day. I want a probability that in a day there are less than 2 claims, which is nothing but probability x is equal to 0 plus probability x equal to 1, right? It is a discrete distribution, so this, but suppose if it had been an continuous distribution, it would be nothing but an integrative part. Okay, so it would be this. So what is the formula of PDF? It is nothing but e raised to minus lambda into lambda raised to x upon x factorial, right? What is my lambda? Lambda is 5. What is x? X is 0. So 0. Similarly, let me do it for here. What is lambda? Lambda is 5. What is x? X is 1. So I would get this as nothing but e raised to minus 5. 5 raised to 0 is 1. 0 factorial is 1. Similarly, e raised to minus 5 into 5 raised to 1 is nothing but 5. Divided by 1 factorial is 1. So I get e raised to minus 5 plus e raised to minus 5 into 5. If I feed this in my calculator, I'll get a probability of around 4%. Okay, this was my first part. Let's go to second part. Second part is the time until the next reported claim is less than an hour. Basically, we want in an hour and we have been given a Poisson process per day. Therefore, here we are going to use this aspect, what we did it right here. So basically, it is nothing but if X follows Poisson with 5 in 24 hours, that is one day, then it follows Poisson 5 into T. What is T? 1 hour out of the whole day, right? So basically now this would follow Poisson with parameter 5 by 24. Okay. I want to calculate my waiting time. I already proved that my waiting time follows exponential with the same parameter. So I can write it here. And what was I asked? Next claim is reported less than 1 hour. So basically, time for reported claims is less than 1 hour. Okay. So this is nothing but my CDF. So what was my formula of CDF? 1 minus e raised to minus lambda x. What is lambda? It is nothing but 5 by 24. What is x? X is 1. So if I feed this in my calculator, I get a probability of 18.806%. So there is 18.806% that the time until which the next claim is reported is less than 1 hour. Okay. So yeah, this is the sum for a normal waiting time one. Now in this lecture, I'm going to extend and what is given in the tables. Okay, this photo which I have extracted is from page number 164 of tables. Okay, and you can see this photo, right? So what does this graph indicates? Sorry guys, I guess there was some problem with my recording. So yeah, let's go ahead. If you can see this part, so how my tables are basically formed. So since you can see that this side is colored, this means that I have been given the probability values for chi-square distribution greater than some values. So even if you can read it right here, it is given for v greater than 3 only. So basically for this page, I have been given greater than values. So if I want to find chi-square for greater than 0.1, chi-square 2 greater than 0.1, I search 2, I search 0.1, this is the value, right? So basically I write that value. Okay. That's how tables are formed. And it has been also stated that for less than 3, the shape applies. For less than v is less than 3. So basically, if my graph would be only colored in the yellow part and it won't be colored here, then basically this means that I have been given the probability of the values less than something. Okay, if the downside portion is colored, it means less than. If the above side portion is covered, it means greater than. This is how you interpret the graphs. Okay, so always read this graph, this line. This would always state what does this indicates. So for different graph, there would be different values. Okay, so this is what it indicates. Now, basically solving for gamma and chi square. How do you solve for gamma and chi square? We will understand that in deep. So suppose x follows gamma with parameter alpha and lambda, right? And what is my f of x? It is nothing but lambda raised to alpha upon gamma of alpha x raised to alpha minus 1 raised to minus lambda x. But if you want the probabilities, then we won't be using gamma distribution at all. How do we find the probabilities then? Basically, we convert gamma into chi square and then we make the interpretation. Okay? Since we have been given less than probabilities for v greater than 3, this means that majority of the aspect we have been given the less than probabilities. Okay, so basically if I'm asked that some chi square is less than some value, then I directly see the table and get my answer. Okay, if I'm asked probability of chi square greater than some value, I basically write 1 minus probability of chi square less than value and 1 minus this answer I would get from tables. This is how I solve. If I'm asked probability of chi square lies between A and B, then how do I solve? I solve this as nothing but probability of x less than B minus probability of x less than A. If you want to understand, we will even understand. Just a second. See, okay, A and B. Okay, I want this probability, right? So how this is true? Let us understand that. So basically, probability of x less than b is nothing but these probabilities minus this probability. So effectively, if I do this, I'm only left with this part, which is what I wanted, right? So therefore, I can say that this is the perfect format to write. And basically, the a and b value could be basically see from tables. We'll solve 1 2 sum so you do not have any problem. Okay. See, then basically if you see my probability values are given in the multiple of 0.5 only, right? But if I'm asked how to find the probability of x less than 0.84 suppose, then how do I find? I find using the formula of interpolation. What is the formula of interpolation? You have to learn this formula, guys. It is very important. It is extensively used. So it is nothing but x minus x1 upon x2 minus x1 is equal to y minus y1 upon y2 minus y1. Okay. Okay, this. So 0.84, I have been given the probability of 0.8 and 0.85, right? So I have been given the probability of 8 and 85. I'll write it here. What do I want? I want 84. Okay. So there would be some probability of 0.8. So if that probability is 0.1, suppose, and this is 0.2, I can basically substitute all these values in this equation, right? And find the value of y. At y would be nothing but probability. So what did I do? I formed a formula for interpolation. If I want to find some value between the two values, I basically write the value of x here and I write the value of probability here, and there would be one unknown value which I could find using substituting here. We'll solve one sum so you will have an idea, so you do not need to worry. So let's solve one or two sums. Let me just have a view over the sums I have copy pasted. Yeah. Hmm. Okay. If I want to find this one, I want to find chi-square 5. I have been given this. I want to find probability of x greater than 6.5. I know my distribution follows chi-square with parameter of 5. So, as I said earlier, for value greater than 3, I have been given the less than probability. So, I will write this in the form of less than probability, right? So, chi-square 5 less than 6.5. Okay, for this, let's see our table's value. Chi-square 5, see, chi-square 5, v is 5 for values less than 6.5. So 6.5 is here. This would be nothing but this value 7.394. Okay, so let me write that 7.394 in my sums. So it would be nothing but 1 minus 0.7394, okay, which is nothing but 0.2606. If I were asked probability of x less than 11.8, how do I solve? I have the value of 11.5, right? And I have my value of 12. Okay, I want the value of 11.8. Y is nothing but my probability. So let me see for what values of 11.5 and 12 we have returned for chi-square 5. So for 5, this line I'm seeing, I want to see 11.5, so this value, and 12 is this value. It lies right here. So it is 0.955779652. Okay, so let me just write it here. It is 0.9577, 0.9652. What was the formula of interpolation? It was nothing but x minus x1 upon x2 minus x1 is equal to y minus y1 upon y2 minus y1. Let us substitute all the values. X is 11.8, x1 is 11.5, x2 is 12, x1 is 11.5, y I do not know, so leave it as it is. Y1 is 0.9577 and y2 is 0.9652 minus 0.9577. So solving this ahead, 11.8 minus 11.5 is 0.3. 12 minus 11.5 is 0.5. Y minus 0.9577. 0.9652 minus 0.9577 is nothing but 0.0075. So let me do this. Therefore, 0.3 upon 0.5 into 0.0075 is equal to y minus 0.9577, right? So if I calculate this further, this part, it would be nothing but 0.0045 is equal to y minus 0.9577. Therefore, y would be nothing but 0.0045 plus 0.9577. What did I do? I took this here. Okay. So I'm left with 0.9622. Okay. That's my answer. 0.9622. Okay. We understood the calculation of chi-square. Now let us understand how we'll do gamma distribution. So for gamma, as I said earlier, we would convert it into chi-square. Okay, so let me write the first step. What is the formula? I will write it. So if x follows gamma with alpha and lambda, then 2 lambda x follows chi-square 2 alpha. Why did I write this? So basically, if you remember, my lambda was half and alpha was v by 2. If I substitute that value, I get x is equal to chi-square v. So this is my point. Why did I want this? Basically, I'm converting this into gamma. So basically, I'm converting gamma into chi-square. So I want gamma is equal to chi-square, right? That's the reason I developed this. If you substitute lambda as half and alpha as v by 2, I get my x is equal to chi-square. So let us understand with one sum. Just saying this would make it much more complicated. Okay, so let us do one sum. You will get an hang over it. See, if x follows gamma with 2 and 1.5, I want to calculate probability x greater than 4. X follows gamma with alpha is equal to 2 and lambda is equal to 1.5. How I write x as gamma? Alpha by lambda, right? So alpha is 2 and lambda is 1.5. So yeah, I just wrote it here only so it won't make any confusion. What was the formula I wrote? I wrote the formula as 2 lambda x is equal to chi square 2 alpha. So let me write it here. Where did the sum go? Here it is. So what was my formula? 2 lambda x is equal to chi square 2 alpha. So what is lambda? Lambda is 1.5 is equal to chi square 2 alpha. What is alpha. Alpha is 2. So basically 3x is equal to chi square with 4 degrees of freedom. Okay. If I were to find probability of x greater than 4, I can only find if this is 3x, right? Because then only I can find chi square and then only I can do further things. So basically now I would be multiplying by 3. What did I do? Multiply by 3 on both sides. Yes, I get this. Now I can say my 3x is nothing but chi square 4. So now I can say that my 3x is chi square 4 is greater than 12. Now this became easy, right? If you see our tables, I want chi square 4 with 12. So leave it right here. So chi square 4 with 12. So which is nothing but 0.9826. I have been given the less than probability. Do not forget, okay, guys? And I am asked greater than 1. See, uh, yeah, I have been asked greater than 1 and answer is less than 1. So I can write this as less than 12, right? I know this answer, which is nothing but what we see from our tables, right? So my answer would be 0.017 something. It would be nothing but 0.174. So my probability that for gamma x is greater than 4 is nothing but 1.74 percentage. Okay, this is how I do gamma sums. Let me do one more sum so you get a hang of it. So if my gamma follows, x follows gamma with parameter 5 and 0.7. I can say that alpha is 5 and lambda is 0.7. I substitute that in my formula, right? This was my formula for 2. What is lambda? Lambda is 0.7. X chi square 2 alpha is 5. So I get 1.4x is equal to chi square 10, right? And if I were asked to find probability of x greater than 10, I could only make a comparison when x is nothing but 1.4x. So let me multiply by 1.4 on both sides. I'll get 1.4x. 10 into 1.4 is 14, right? This is multiplying 1.4 on both sides. Now I can write this as basically chi square 10. So now I can write this as chi square 10 is greater than 14, right? Chi square 10 greater than 14. I will see my tables one. So let me see the tables. Chi square 10. So my 10 is here. And where does my 14 lies? It lies somewhere here. So basically 0.8270 is my answer. Okay, 0.8270. Yeah, and this is my less than tables. So I need to take care. It would be 1 minus probability chi square 10. So now I can see this value from my tables. Okay, what did I see? 0. I forgot. Yeah, I have to see it again. It's okay. 10 and 14 somewhere lies here. So let me just zoom it out. So it would be 0.8270. Okay. Hmm. Yeah, it would be 0.8270. If I feed this in my calculator, I get my value of 17.3 percentage. So there is 17.3 percentage that my gamma distribution would be greater than 10. Yeah, this is how you do. And we are done with gamma and everything. Now in the next lecture, we will starting with a new distribution. So yeah, bye bye.